Yes, good morning, everybody. Today we are going to learn the joint distribution in case of two random variables. We have learned the distributions, probability distributions for the case of a single random variable. Now, if we need to take two random variables simultaneously, then that will be known as the joint distribution between these two random variables, which is associating these two random variables. Okay. And the joint distribution will go on like this. We are going to learn first that what is the structure of the distribution, probability distribution in case of joint in case of two random variables, right? So first, let us take x to be a random variable, which is assuming the values like x1, x2, as you see on the screen, that x is taking a random variable x we have taken, which is assuming the values x1, x2, x3 up to xm. Then we have taken another random variable y, which is again taking some other values like y1, y2, y3, yn. So there are m number of random variables in case of x. For the case of x, m number of values are there for x random variable, and for y there are n number of values. All right. Now, if we are going to write the joint distribution, then the table will go on like this. Look at the table if you can. That. Yes, this will be the table for the joint distribution of x and y, where these x1, x2, x3s are the values of the random variable x, and y, values of the random variable y, will go on horizontally. And the table, which the entries of the table will gives us the joint distribution values like the x1, y1, x1, y2, x1, y3, like x1 and y1 position, it takes x1, y1, x1 with y2 position, it takes x1, y2, x1 with y3 position, it takes x1, y3. Likewise, it is going on up to x1, yn. Similarly, if we go for the second row that starts with x2, x2, y1, x2, y2, x2, y3, up to x2, yn. And likewise, we can populate up to xm. So the total variable, joint distribution variate we have got. These mn number of the variate that we have written, the entries of the table rather we can say, these are m into n in numbers, as m and n random variables, two set of random variables are there, each containing m and n numbers respectively. So these entries are m into n in numbers, consisting the values in the form of xi, yi, and this table which contains these entries of the two set of random variables is known as bivariate data. All we know that bi stands for two, so it is two sets of random variables we are taking over here, and that's why it is the bivariate data. Now we are going to learn next that this is the structure of the bivariate data. Now, how we can populate, or how we can write, or how we can obtain the probability, corresponding probability distribution rather, from here, from the set of bivariate data. So let us move on for that. First, I'm writing over here Pij. What it denotes? Probability of assuming the pair xi, yj. That means in this table, each entry, probability of getting this entry xi, yj, that probability is denoted by Pij, P suffix ij. And that will be obtained as P xi, yj. Actually, the probability having the entry xi, yj as a set of random variables, and that will be obtained as probability, or that will be read as, rather you can say, probability x equals to xi, probability y equals to yi. If you can see, if you remember that whenever we have deals with the single random variable, I'm going to the whiteboard to make you understand that whenever we have taken the case of a single random variable, at that time, our distribution will go somewhat like this. We are writing it as fx, and fx is having some distribution if it is binomial, if it is Poisson, like this. What does this fx stands for? This fx is either will be our probability mass function if it is a case of discrete random variable, or it will be the probability density function if it is the case of continuous random variable, and discrete random variable. All right. Now, this fx, which we sometimes say probability mass function for discrete random variable and sometimes say probability density function for continuous random variable, what does this stands for? This is not a simple function of x. All we know that this is nothing but probability that the random variable x takes the value small x. This probability is denoted as like fx. This is not a simple function of x. It is actually a probability. So the same thing is going on for the bivariate data also. We are denoting it as Pij, which is actually probability xi yj, probability of getting xi yj, or else it will be probability that the random variable x takes the value xi and the random variable y takes the value yj. All right. So this is nothing but it is a notation for Pij, and that's what written over there in the note. So let me share it once again where we are. Yes. So this is the set of probability distributions. Now we are populating the table for the probability distribution of the bivariate data. In the previous table, we have seen that is a table for bivariate data. Now we are moving on for the probability distribution of bivariate data. See, again, we have written x and y random variables, x vertically and the values of the random variable y horizontally. Now, this P11, what does it signify? P11 means probability that x equals to x1, y equals to y1. P12 means x equals to x1, y equals to y2. P13 means x equals to x1 and y equals to y3. So likewise, we are writing all the probabilities for corresponding to a particular pair of a bivariate data. These entries are nothing but the probabilities corresponding to a particular pair of the bivariate data. All right. Now, look at the extreme right side of the table and the below part. At the extreme right, what we are writing it as Px1. This Px1 is actually the sum of the row 1 probabilities, the sum of the probability entries in row 1, that will be denoted as Px1. Sum of the row entries in sum of the probability in the row 2, sum of the probability entries in row 2, that will be denoted by Px2. Likewise, it will be going on. So sum of the rows of the entries of the table, that will be taken as the extreme right hand side, Px1, Px2, Pxm. And if I take vertically the sum according to the column of y, that is P11, P21 up to Pm1, that will be Py1, P12, P22, Pm2, that will be denoted as Py2. And likewise, it will be going on vertically, right? So this is what where row wise and column wise total are Pxi, as I have told you just now, and Pyj is the sum of the vertical entries of the probabilities. And the grand total, that means this vertical as well as this horizontal entries, if I make the total, if I take the total of this one, that will gives us the total probability, and that will always be equals to 1. That we know that the value of the total probability will always be equals to 1. So these two tables, whatever we have seen, represent the joint distribution of the bivariate data. The row-wise totals Pxi and the column-wise totals Pyj are called marginal probability mass functions of x and y respectively. Marginal probability mass function of x and y variable, random variable respectively. As small Pij, as we have seen earlier, that small Pij denotes probability x equals to xi, probability y equals to yj. It is known as the joint probability mass of the variate xy. And this extreme left hand side sum and the horizontal sum are known as marginal probability mass. All right. So we have seen from the table, now it will be clear to us that which will be the marginal one and which will be the probability mass of the variate. Now for the individual variables, if I take the variable x and y individually, probability x equals to xi, that is pxi, pi1, pi2, pi3 up to pin. Similarly, probability y equals to yi will be pyi, P1J, YJ actually it will be. So P1J, P2J, P3J, PMJ. So X will have the probability distribution. If you are going to find the probability distribution of X only from the joint or the bivariate data, how can I write that? X, the values of the random variables x1, x2, x3, xm, and then pxi, that means probability x equals to x1 will be, that will be given from the table of the right extreme right hand side. See, pxi is px1, px equals to x2 is px2, x equals to xm is px1. So writing these corresponding to the variables, this is known as the marginal distribution. Look at over here, marginal distribution of x. Similarly, if we write the variables, random variables y value, and horizontally the total sum of the pyj's, then that will give us the marginal distribution of y. So in this way, we can write the bivariate data, bivariate probability distribution, marginal distributions of x and y respectively from the bivariate probability distribution, whichever is given to us. Now come to the concept of independent random variables. If we have two set of random variables, then when they are said to be independent of each other, if Pij can be written as Pxi into Pyj, or else you can say it as Pij means Px equals to Xi, Y equals to Yj. And that will be equal to Px equals to Xi into Py equals to Yj. Then only we can say that the two random variables X and Y are independent. All right. Now let us come to a particular problem which will clarify the theoretical part what we have learned till now. So look at the problem. What it says that let x and y be a bivariate having the following joint distribution. So x and y is a bivariate data given to you, which is having the joint distribution as given in the table over here. So values of x are 9 and 0.2 and values of y are -3, 5, 7. Now from the table, we can see that whether they are independent or not. First, I think they have seen that only, that probability x equals to 0.2, and if I take y equals to 5, then what it will be? It should be the multiple of these two, probability x equals to 0.2 and into probability y equals to 5. So all we can see from the table that x 0.2 and y equals to 5, x 0.2 and y equals to 5, that part is 0.35. And if I take the multiple also, it becomes 0.35. So for this pair of bivariate data, it will be independent. But this is not true for each and every pair, because if I select the another pair where x equals to 9 and y equals to 7, at that time my pxi or pij will be 0.06. But probability x equals to 9 into probability y equals to 7, what it is? 0.30 into 0.20, as well as it is also 0.06. So we can see that whatever the joint distribution is given to us in this particular problem, that in that joint distribution, the variables, the random variables rather you can say, the random variables are independent random variables. Since for each pair of Pij, we can take it as Px equals to Xi into Py equals to Yj. So we can conclude from here, from this particular problem, that the two random variables in this bivariate data are independent. Achha. Let us come to the next. Let's see what is going on over here for this particular problem. For independency, Yes. So let us see the next problem where the bivariate data is given to us as the values of y are 3, 5, and 8, and the values of x are -1 and 4. And the distributions, probability distribution, the values of probabilities corresponding to the bivariate pair is given to us as like this. Now from here, if we need to obtain the marginal distribution of x and y both respectively. So what it will be for x, the values are -1 and 4, and the corresponding pxi's are what? For corresponding to -1, it is 0.4, and corresponding to 4, it is 0.60. So we can write it as x and corresponding probabilities that will gives us the marginal distribution of x. Similarly, if I go for marginal distribution of y, it will be the values 358 and the corresponding horizontal total, that is 0.04, 0.4, sorry, 0.40, 0.40, and 0.20. So these are nothing but the marginal distributions of x and y. Now we can go for their independency. What it shows, let me, yes. For the pair of independency, for independent, we need to check out each and every pair. If at least one pair, for one pair of bivariate data, it is not independent, that means the total data is not independent. So let us take px equals to -1, y equals to 8. We can see that its value is 0.05 from the table. But if I take px equals to -1 into py equals to 8, then the multiple gives us the product gives us 0.08, which is not equal to the probability x equals to -1 and y equals to 8 at 0.05. So we can conclude from here that the pairs are of random variable in this bivariate data are not independent, right? So in this way, we can obtain the marginal distributions. We can discuss about the independency of the bivariate data of the random variables given in the bivariate data. Now, this is a problem which covers out the total part, that is an urn contains 3 red, 2 white, and 3 blue balls. 3 balls are drawn from urn X and Y. Denote the number of red and white balls in a draw. Find the joint distribution of X. Hence, find the probability X less than equals to 2 and Y greater than equal to 1. Find the marginal distribution of Y, and hence find the probability of drawing more than 1 white balls. And then we need to conclude that whether X and Y are independent random variable or not. So look at the problem carefully. What does the values, random variable values X and Y will be? What does the values of X and Y? Random variable X takes the values. Actually, X is denoting the number of red balls. So how many red balls are there over here? We can see that it is containing 3 red balls, right? So random variable X can take the value 0, 1, 2, 3. And what about the Y? Y denotes the number of white balls. So how many white balls are there? We can see from there it contains 2 white balls. So the value will be 0, 1, and 2. 0, 1, and 2. So these are the values of the random variables. Now what else is given to us? See, what we need to do? Find the joint distribution. So how will I get the joint distribution? See, first values of y horizontally 0, 1, 2, and values of x vertically 0, 1, 2, 3. Now what? Probability 0, 0. So x equals to 0, y equals to 0. 0, 1 for x equals to 0, y equals to 1. Likewise, we have written in terms of probabilities. Now, one by one, we can find out the probabilities. And then we need to put on the values over there. Then only our work is done. So let us do that on the whiteboard. If you can see, if I can see a particular one, P00. What does it stands for? Probability x equals to 0, y equals to 0. X equals to 0 means the red ball will be 0. And probability of no red balls, no white balls. X is the number of red balls, Y is the number of white balls. So no red balls, no white balls. What does it means? Probability of 3 blue balls. Because we are drawing 3 balls at random. Look at that. Look at the problem. 3 balls at random. And no red, no white. That means all three balls are blue balls. So probability of getting all 3 balls are blue balls among the 5 is 5C3, obviously. So it is 5C3 divided by the total number of balls are 10. So 10C3. So it's 10 by 120, that is 1 by 12. So this is a corresponding probability P00. Likewise, we can find all the probabilities of the entries, given entries over here. And ultimately, we will get the table as probability distribution table as like this. This is our probability distribution table. All right. Now we need to find out the particular problem where probability x is less than equals to 2 and y greater than 1. I mean, what the values x can take? 0, 1, 2, and y can take 1 and 2 because maximum value of y is 2. So 1 and 2. So x equals to 2, y equals to 1, x equals to 2, y equals to 2, x equals to 1, y1, x equals to 1, y2, again x0, y1, x0, y2, right? And taking the sum, we will get the required probability. All right. And then comes the marginal distribution. All we know now how we can write the marginal distribution of x and y if the probability distribution of table is known to you. And you can see from the particular pairs that they are not independent. So this clarifies the total problem of independency, which contains the concept of independency, marginal distributions, as well as the probability distribution table, preparation of probability distribution table, and likewise a particular probability also we have found. So in this way, this is all about the concept of joint probability distribution, rather bivariate distribution. What we have seen, the bivariate distribution, what it is, which is containing two variables, and how we can obtain the corresponding probability distribution for that bivariate data or bivariate distribution given to us. Next, some of the independent random variables. Yes. Next, we can move on to the part of expectation that we have seen already for single variable. Now, we need to evaluate the expectation for bivariate data. See if x and y be the bivariate having joint probability mass function. That means we are going for discrete random variable. So probability mass function is given to us as Pij, probability x equals to xi, y equals to yj. And then expectation of xy is denoted as expectation of phi xy, which is equals to double summation. First summation over I, summation over j, Pij, that means corresponding probability for the pair ij, xi, yj, into the function phi xi, yj. And similarly, if I need to obtain phi x only, then it is expectation of phi x. For phi x only, expectation of phi x, it will be summation over all I, phi xi, that means marginal distribution, and pxi, probability corresponding to that marginal distribution. Similarly, expectation of phi I will be summation over j, phi yj, pyj. So let us take a problem. For this joint distribution of xy, we need to obtain some expectation values, say expectation of x square y. So what we will take, both the variables are there. So the double summation will go. I is going from 1 to 2 and j is having 3 values because corresponding to y. So x square yj pij. Now summation I equals to 1 to 2 x. First we will take the summation over j, and then we will go for I. Okay. Taking the summation over j, we will put on the values of j P11, P12, P21, P12, P22 like this. And taking the whole summation, we will be getting the corresponding values. Similar is the case for expectation of x cube. As it contains only one variable, so it is xi square pxi, which is the marginal probability distribution, and will go accordingly. Similarly, for y, expectation of y plus 2, it will contain only one variable y. So marginal probability distribution of y will go on over here. So these are the concept of expectation. Now, as we have learned some theorems or some properties of expectation for the single variables, the same will continue over here also. The proofs are given. You can go through the proofs, like expectation of x plus minus y equals to ex plus minus ey. Expectation of, that means expectation of the sum of two random variables is equals to sum of their expectation. Expectation of difference of two random variables gives us the difference of their expectations. Okay, and the proof is given over there. We can go through the proof from the notes that I'll be providing over here. That is, if you take expectation of x plus minus y, then according to the definitions, and it contains two variables, so double summation it will go I varying from 1 to n, j varying from 1 to n, xi plus minus yj pij. Now simplifying it, xi pij plus minus yi pij, it takes xi pij, yi pij, summation I over I xi, summation over j pij, summation over j yj, summation over I pij. Now summation over I xi into summation over j pij gives us pxi, the marginal density, probability distribution of x. Similarly, summation over I pij gives us the pyj, the marginal probability distribution of y. And this is what? This is expectation of x, as we all know. And this is expectation of y. Similarly, expectation, that's why expectation of x plus minus expectation of y. Similar is the next two properties. Expectation of product of two random variable is product of their expectation, provided obviously x and y are independent, otherwise not. And k, if k is a constant quantity, the expectation k will come out and the expectation of the rest of the quantities will follow. So this is all about the expectation for the random variables or for the bivariate data, which we have learned till now.